Hello everybody, and welcome to the first of many geometry videos. So, today we are going to be discussing section 1.1, the very first section of the class. One thing I want to mention about geometry that makes it fundamentally different from algebra is, in geometry, one of the most important things is knowing your definitions. Knowing how we define things such as a point, a line, a plane, will carry you through the class, and more vocab is going to stack up throughout the year. So I recommend keeping an organizer to hold all of your vocabulary terms. Again, these will be coming up time and time again. So let's get started. One word that you're probably very familiar with is a point. A point is this, just a single dot. Because a point is just that, an incredibly small dot that is basically supposed to be too small to even see, we say that it has no dimension. A point has no dimension. It is a dot. So when we say something has no dimension, what does that mean? Well, you may have heard of objects like three-dimensional objects. For instance, this pen that I'm using is a three-dimensional object. Not only is does it have a length, it also has a width, and if I flip it up this way, you can see that it also has a depth. Three-dimensional objects can be described with three different directions: length, width, depth. A two-dimensional object is something that can only be described with two different qualifying adjectives. So this piece of paper, for instance. This piece of paper certainly has a length, it certainly has a width, but it doesn't have a depth. I mean, if you want to get technical, you could say it has a very, very small depth, but for the purposes of this, we could say that this is a two-dimensional object, something that has two dimensions or two directions. We're going to talk about a one-dimensional object in a moment, but a point doesn't spread out in any direction. It doesn't have a length, or a width, or a depth, or anything. That's why it is one-dimensional. When talking about points, we want to keep track of them, because throughout the class, you might have many points in a single place. Take a peek, for instance, at example 1. Down here, there are a ton of points all over this diagram. So you'll see we actually label these points with capital letters. I'm going to call this dot A. When labeling a point, or talking about a point, we would just call this point A. Alright? Let's upgrade this a little bit. Instead of just having a point in the middle of an empty space, what if we were to make a line? Now, many of you know what a line is from Algebra 1 and before. But there are a couple of key features that I really want to talk about with regards to a line. First off, a line has one dimension. It has a length. Or, because of these arrowheads, we know that it has an infinite length. Yes, anytime you see an arrowhead, it means that that particular figure is going on and stretching in both directions forever. I mean, it goes off this way and off the page onto my desk, and stretches this way through our other definitions. It goes on forever. A line has one dimension because it only goes in one direction. It is represented by a line with two arrowheads. There we go. It is represented by a line with two arrowheads. And again, that just shows that it goes on forever in both directions. Now, with lines, there's something else that we will need to put on here, because we don't have a way of giving this line a name. let's work backwards for a moment and actually see if we can start with a point and make a line. So let's say I started with point, let's call this one point C. No reason, I just like the letter. If I was to ask you, hey, what direction is the line that goes through point C? There probably wouldn't be a way for you to tell. I mean, you might make some predictions, sure. Maybe you say, oh, the line might go this way through point C. Or you might say it might go this way through point C. Or it could go straight up and down. We don't know what direction there's going to be, or what direction point C is going to be going in. Instead, we have to think about lines as having more than one point. If I told you the line doesn't just pass through point C, but it also passes through a second point, we'll call this one point D, now there's only one way the line can go. The line has to go through both of them in this direction. We've discovered that every line, in order to basically name it, has to have at least 2 points. So, on our line, let's put 2 points. Let's put one right over here, and right over here. I'm going to name these 2 points 2 different things, since, they are separate. So I'll name the first point A. I will name the second point B. If we wanted to talk about this line, we can now say, oh, this is the line that goes through A and B. For shorthand, there is actually a better way of writing this. The shorthand way of writing this is as follows. If we want to describe the line that goes through A and B, we would write it out as A, B, with, and this is the important part, a double arrow-headed line above it. This literally reads line AB. That's what this is. Can you think of another name that we might be able to give this line? Let's say if somebody was looking at it from a different direction. If you said we could call it line BA, you are absolutely correct. Because think about it. This line is supposed to go off in both directions, to the left and to the right. If it goes on forever, who says we have to start at A? We could start at B and look to the left, and it's still the same line. So line AB is the exact same as line BA, or you might also see another shorthand way of writing it. Instead of writing out the letters like this, the shortest way to write out the name of a line is to give it its own letter, kind of like how we have point A up here. However, instead of using capital letters, because we don't want to confuse people, we use cursive lowercase letters. This is the cursive lowercase letter L. This little symbol here means line L. So that is the exact same thing as these two. If you see a cursive letter next to a line, that is the name of the line. If you have any difficulty reading the cursive letters, let me know. I would be able to help you. Next up, we have a plane. And before we draw anything, no, it's not that kind of plane, as cool as it would be. We started talking about an object that has no dimensions. We talked about an object that has 1 dimensions. It only makes sense that we are now talking about something that has 2 dimensions. And eventually in this class we'll talk about something that has 3 dimensions. That'll come a little bit later. So a plane has 3 dimensions. Whoops. Sorry, 2 dimensions. What am I saying? I just said 2 dimensions and that we would talk about something that has 3. Got a little distracted. There we go. A plane has 2 dimensions. What that means is it has a length and it has a width too. Didn't we talk about something that has a length and a width? Like this piece of paper? This piece of paper has 1 direction here, the length, one direction here, the width, and it looks like every other part of it is a combination of some length and some width. Since it has two directions, it has two dimensions. A plane is a flat surface. Imagine, if you will, a concrete parking lot, but that parking lot stretches on as far as the eye can see. That would be an example of a plane. It's flat. You can stand on it. There's no real texture to it or depth. But it does go on forever. So when we showed that a line went on forever, we could draw little arrows on it. It's a little bit trickier to show that a plane goes on forever. In fact, we usually don't show that a plane goes on forever. We just assume that it will. To draw a plane, all you need to do is draw a parallelogram. Now it's going to require some visualization. Could you imagine this parallelogram as being a piece of paper that's slightly slanted like this? That is what we talk about when we see this symbolism of a plane. It's like a piece of paper that's at a certain angle. The angle itself isn't important, but what matters is that you can see that this is supposed to be a plane. It is represented by a shape that looks flat. Now, we have a little bit of a problem here. I'd like you to imagine a couple of points on a plane. So let's say this is our plane, and I have a dot here and a dot here. Well, we can very clearly see that makes a line because 2 points make a line. But does it make a whole plane? Unfortunately, it does not. The reason is, with just 2 dots, you only get one direction. If you wanted to get a plane, you would have to add a 3rd dot. And now we can say, oh, this plane is the one that has this type of surface in it. A plane is something that can hold this entire triangle. So that's why this piece of paper is a plane. 3 dots that are not on the exact same line make a plane. So let's make 3 dots. 1, 2, and 3. Let's also label those dots. I'm going to call them, my naming structure is pretty predictable, A, B, and C. With this, we now have plane ABC, and we label it as such. We just label it as plane A, B, C. No need for any fancy symbols like the line. There is one more way to label this. Much like the line, we can use a letter to represent the entire plane. But there is a catch, and I don't like this catch very much. The catch is, instead of using a cursive letter, which would make a lot of sense, we just use another uppercase letter, such as M or B. Well, we can't use B because we have point B, but maybe Z or X. All of those can also be used to label a plane. So if you see a capital letter that doesn't have a point attached to it, that capital letter is labeling the entire plane. This could also be called plane M. All right. Almost done with the vocabulary for this first part. I now want to talk a little bit about collinearity and coplanar points as well. When you see the word linear, what does that make you think of? Linear means line. Co means together, like cooperate or co-worker or coexist. Collinear means points that work together on a line. It's basically just a bunch of points that are on the same line. In order for you to have collinear points, they have to be points that, oops, my pen is dying, I apologize, lie on the same line. Bam. So, if I was to draw maybe some points like so, I could make a couple of collinear points. Once again, I'm going to stick to the tried and true naming scheme of A, B, and C. We'll be doing some more fun stuff in the future. Whoops, used the wrong color, I don't want to confuse myself. A, B, and C. We know, however, that these 3 points don't lie on the same line. I mean, think about it. I could draw a line through A and B. Those 2 would be collinear, but then C would be left out. I could draw a line between B and C. There's definitely a line that connects those 2, but then A would be left out. I could draw a line between A and C, but then B would be left out. No matter how I draw it, one point is left out, meaning that one point is always going to be non-collinear. In this example, B is not collinear. A and C are collinear points. Similarly, let's say we have a plane. I'm going to draw this one a little bit smaller. Let's say we have a plane with 3 points on it, because you're required to have 3 points to make a plane, and also 1 point floating off in the air somewhere. Again, I'm going to label these points A, B, and C. And I'm also going to name the floating point D, for, dang, that point is floating away. Well, coplanar then must mean that points that are on the same plane. And it means exactly that. Coplanar points are points that lie on the same plane. A, B, and C are all partying together. They're all on the same sheet of paper, kind of like these 3 points that we drew before. Point D is floating off in the middle of nowhere, doing God knows what. That means A, B, and C are coplanar. D is non-coplanar. So far, so good, right? Well, let's put it to the test. I'd like you to take a look at example 1. Try this one out on your own and pause the video while you do so. Please do so now. I apologize, that was the bell, but it was also the signal for let's do this together. Hopefully you had a chance to actually try these problems out. If we're asked to name 3 points that are collinear, we're looking for 3 points that are on the same line. There are only 3 points that are collinear in this diagram. Points D, E, and F are collinear. So I'm going to say points D, comma, E, comma, and F are collinear. The commas are important because we want to make sure we're separating these points. People want to know that, hey, D and E are separate points. There's not some weird mutant point named DE. Similarly, we're asked to name 4 points that are coplanar. This one, there was a little bit of a trick thrown in. We want to name 4 points that are all on the same plane, and thankfully, there is like one plane shown here. The plane has the points G, D, E, F, and the letter M. Be careful. Notice how there's no dot under M. That's just the name of the plane. The 4 points that are on plane M are points D, E, F, and G. Very nice. Last but not least, we are asked to name 3 points that are not collinear with each other. That means none of these 3 points are connected by a line. Well, let's think about it. We've got a point that's sort of floating off in the distance over here, so that's an easy one. Point G is definitely not collinear with anything. But then we have a bit of a predicament. And in fact, we have a lot of options. We want to name points that are not on the same line. H seems to be floating pretty high above the others. It's on the same line as E, but it's not on the same lines as D or F. So you could say G, H, and F, or you could say G, H, and D. You could not say points G, H, and E because H and E are collinear. They're on the same line. Very nice. Let's talk intersections now. We now have basically the words of our geometry recipe. Now it's time to start putting them together and see what we make. Intersections are just whenever 2 things cross. So, when it asks what the intersection of 2 lines is, let's look and see what happens where they cross. Well, when these 2 lines cross, they cross at a single place. What do we call a single place like that? It's a point. It's something that has no dimension. It's just a place where they cross. Perfect. The intersection of 2 planes is a little bit difficult to understand. I mean, when you think about it, we basically got an infinite flat space crossing over another infinite flat space. Maybe a good way to think about it is if you had an infinite floor crossing an infinite wall. Another way to think about it is if we have 2 planes here. So here I have 2 pieces of paper. I think we would all agree that these are both planes. They don't really have a depth to them. I mean, they have a microscopic depth, but they just have 2 directions. They go longwise and they go widthwise. However, if I was to make these 2 suddenly cross into each other, pass through each other, what is happening where they cross? It's a bit of a tough question because this looks like a freaky shape no matter which way we spin it. I mean, look at this. We've got sort of like a cross shape here. We've got some weird shape on this side. We've got weird shapes on all the sides. Well, no matter how you look at it, it looks like it's not a point that it's making because they're crossing at multiple points. In fact, they're crossing at infinitely many points along this area. So what do we call that? What do we call something that goes on in one direction infinitely? Everybody, when 2 planes cross, we get a line where they intersect. Or at least we would if Mr. Strayer could draw. There we go. We have just a straight line where they cross. So, the intersection of 2 planes is a line. What about if I had a line and a plane? So I'm going to take one of my planes from earlier. Let me just take this one. Here it is. And what happens if I was to push a line through it? Well, let's watch what happens if I push a line through it. Let's pretend that this marker, or this pen I should say, stretches on forever and is a line. Well, when it goes through this particular piece of paper, I shouldn't have chosen cardstock for this portion, but if we were to pass it through, what is created? Well, it's like a little bit of a hole, or a point. When a line crosses through a plane, you end up with just a point. It only crosses at one spot. That's how you get a point. Very nice, everyone. Let's flip over the page. Let's tackle page 2. So, now that we've talked a little bit about points, lines, and planes, there are different types of lines that we will also need to distinguish. There are line segments, rays, and even something called an opposite ray. Because we can actually talk about these and define exactly what they are, we call them defined terms. We really can't define a point or a line or a plane because they're infinite and they don't have a strict definition. These ones do. Let's start with a line segment. Imagine, if you will, a line, except instead of two arrows going off in both directions at the very ends, it actually stops at 2 points. If you have a line that stops on one end and at the other end, you have a line segment, not a full line. We use line segments quite a bit, so here's a formal definition of it. A line segment, specifically line segment AB, is defined as what consists of the endpoints A and B and all points between. Line segment AB consists of the endpoints A and B and all points between. First off, we should talk about what an endpoint is. It's a pretty obvious definition, but an endpoint is a point where something ends. In this case, our endpoints are where this line segment ends. Because we want to still be able to name this thing, we should still talk about where it starts and where it ends. We could start at point A and go over to point B, but because it doesn't stretch on forever, and we don't go through point A or through point B, we just want to put this type of line above AB. This actually means line segment AB, not line AB. Remember, line AB on the previous page had the arrows because it went on forever. Here, we just call it line segment AB. But the rule still applies. Because starting from A and ending at B is the exact same thing as starting at B and ending at A, we could also call this line segment BA. You might occasionally see line segments labeled much like lines are, but it's not often. Most times we really care about those endpoints. A ray is like a blend between a line segment and a line. Think about if we had a starting point, but we didn't really have an ending point. So we always need 2 points no matter what for any type of line. Let's say it starts on this first one, but then goes off, follows its dreams, never ends. Well, we would be left with what is called a ray. Think of it like a ray of sunshine. The rays come from the sun and hit the earth, or go off into space forever. They don't go backwards back to the sun. A ray has only one direction. It's just going forwards in one direction. So, a ray, specifically ray AB, consists of the endpoint A and all points on the same side as B. So even if I added a third point down here, point C, or a fourth point, or a fifth point, that's still the same ray because it starts at endpoint A and it shows all the points on the same side as B. You might have predicted it, but if we are labeling a array, you want to see where we start. Since we start at A, that'll be our first letter. That's our endpoint. It goes through B, so B will be our second letter. And we draw it with an arrow starting from A and going towards B and through B, like this. Now, here's a question. Previously, we've been able to have AB and BA be the same thing. Is that the same case here? Does AB equal BA? Is ray AB the same as ray BA? Take 10 seconds and try and take a guess. We may see that in fact, AB is not the exact same thing as BA. Big X. No, 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 not the same. Because think about it. AB is the ray that starts at A and goes through B. Ray BA would be a ray that starts at B and goes through A. It'd be going in this other direction. Rays can't be switched around the same way that line segments and lines can. That said, there is one more definition to talk about, which is opposite rays. Imagine, if you will, we have a mysterious and fantastical point A right in the middle of our definition here. We then make a ray through a equally mysterious but slightly less mystical point B, like this. It goes from A through B. Cool, that's just ray AB. But let's say we added a third point in the other direction from A. Let's call it C. Well then, we've got two rays. One ray starts at A and goes through B. One ray starts at A and goes through C. Those are opposite rays, and you'll see that they look a lot like a line with 3 points on it. In fact, for all intents and purposes, this is a line. This is just line BC, or BA, or AC, or whatever order you want to put your 2 points in. But it's expressed as two rays connected at their endpoint. Opposite rays are two rays connected at their endpoints. Oops. To make a line. Well, how do we label this? We label it as having two different rays. Like we said, we start at A and go through B. That's one of our two rays. So ray AB will be the first part of it. We then put the word AND in between and write out our second ray, which goes from A and through C. So it's ray AB and ray AC, like that. So that is it for the actual notes portion. Now you've got some practice problems. I do want you to pause the video here again and try all of these problems out from these examples. We'll come back and talk about it in just a moment, but I want to give you a chance to try it. Pause the video now. All right, let's talk about these examples. So, if we're asked to correctly label this one, first off, what is it? Well, it's a ray. It has an endpoint, but it also has an arrow in the other direction. So no matter what, it's going to be a ray. When labeling a ray, we always want to have our endpoint be the first point. And if we look at the diagram here, it looks like it starts at B and goes through A. So this one actually would be ray BA, like so. B is a little bit easier. Question B just has 2 endpoints. Well, we know what that means. When there are 2 endpoints with a line connected between them, that's just a line segment. So, we could have our line segment start at C and go to D, or you could flip it and have it go from D to C. Either way, you would be writing it as a line segment. Either line segment CD or line segment DC. If we look at example C, this one actually has many different answers, and I mean many of them. The first way we could look at this is we could say, oh, this is just a straight line. And we can use our line labeling rules from earlier. I mean, we could call this thing a line with any 2 of these points. We can call it line SO. We could call it line OS. We could call it line OX. We can call it line XO. We can call it line SX. We can call it line XS. All of those are ways of writing it as a line. But many of you may have actually labeled it as opposite rays, which is how I personally would have seen this one. If we take a look at this, O is our central point. So we have 2 different rays. One that starts at O and goes through S, one that starts in O and goes through X. So you can also label it as opposite rays, OS. The arrow direction does matter. It has to start at O and go towards S. Otherwise, it'd be going the other direction. And ray OX. Just a quick note before we move on to the next one. We don't usually like to put the arrow facing the other way. I mean, y'all already have enough to worry about. The last thing you need to worry about is which way the arrow is going. Just like how in math we wouldn't want to put x3, we would want to put down 3x to represent 3 times something. We don't really want to have the arrow go the other way, even though it's technically correct. It's just a lot to handle. So let's take a look at example 3. Example 3 is just a drawing exercise. So if we're asked to draw a line AB, it's a line because it has the 2 arrows, we should start by putting down a point A. We should put down a point B. I'll make mine slanted like this, but you could have made yours in whatever direction you wanted. As long as the line connects both of them and has the 2 arrowheads at its ends, it's a line. Similarly, for ray AB, we know it's a ray because it only has 1 arrowhead. This one, we want points A and B, but this time we have to start at A and go through B. That's what the arrow direction is telling us. Otherwise, we'd have BA, like up here. So, we start at A, go through B, there's ray AB. Finally, for part C, we have line segment AB. This one is the easiest of the 3 and probably the most common we'll see throughout the course. It is just 2 endpoints with a line in between them. Fantastic. Last but not least, we had example 4, which is to match each letter to its correct number. Let's start with A. A looks like it is ray, starting at P and going through R. If we look at our diagrams here, there are 2 rays. One that starts at P and goes through R, one that starts at R and goes through P. So this one is a very quick solution. We know that A has to be 2 because this is the only one that starts at P and goes through R. The answer to letter A is number 2. Letter B is line segment PR, and only one of these is a line segment, so that's another sort of freebie. This is the only one that doesn't have an arrow. So number 3 is B. Third, we have C, which is line PR. This one can be a little tricky. We see that all these have PRs. This one has a double arrowhead, but there's an M here. wouldn't this be line MR or MP? Well, again, you only need 2 points to make a line. Anything else is just extra. So this is still line PR because it's a line and it goes through P and R. So number 1 does correlate to C, or correspond, I should say. Finally, by process of elimination, we know this one. But for letter D, we're starting at R and going through P with array. Number 4 is the one that starts at R and goes through P. Done. Thank you so much, everybody. That concludes section 1.1. You did it. You made it through the first one. Have a fantastic rest of your day, and I will catch you next time. See ya!